because I was about to say I did some intelligence, but Paul basically stole me the show because everything is on this slide. So Paul leads the group on software performance optimization and is also a co-director of the Center for Computational Methods in Science and Engineering. So Paul is working, if I generally summarize that, on all kinds of areas of making parallel computing more simple. And in one or the other sense, that's probably what most of us in this room strive for. So it's my pleasure to introduce you Paul Kelly for his talk on using domain-specific languages and access execute descriptors to expand the parallel code synthesis design space. So I'm more than curious what this title, what's behind this title, and particularly what access execute descriptors are.
Thank you very much for your introduction and your kind invitation indeed. It's a great pleasure to be talking to you today. My PhD many years ago was all about parallel functional programming, and so to be returning to a functional programming conference is a pleasure and in a sense an irony in that I stepped away from the functional religion and strayed. I would claim that there are in some sense functional language, functional principles underpinning things, and I hope that as we go through you'll see some of them emerging. It was kind of comes to introduce my work as making parallel programming easier. I'm not sure it's always easier I'm interested in, and we might reflect upon that too. So, the first thing I should do in introducing this slide is to promise that I'll explain the title. The access execute descriptors will come up as a middle layer in some of the abstractions that I'm talking about, and we'll get to that. Much of this talk is really about the whole kind of domain-specific language agenda, and I hope that you will think of my talk not so much as delivering my research results as offering things to prompt you in thinking about what you might do and what you think about these things. The other thing I have to say is that practically everything I'm going to talk about is really the work of people I work with. And there's a great big list of them here. In fact, one or two of them are in the room today. Mike Giles in particular from Oxford is, I think, here. And indeed, some of the things I'll talk about are very much to do with engagements with computational scientists, in some sense applications people. I'm not the expert. I'm here to try and talk to you about our efforts in engaging with them, and sometimes I'll be talking about things which are really their side of the table. So, I have to admit this is a slightly discursive talk. I'm going to talk about some of the big picture context, and I'm going to try and talk around some of the things that I think are important with specific examples from what we've done. But in a sense, the specifics are not the important thing. Let me begin with this, because it's one of my favourite things. And forgive me if you've seen it before, because I've used it before. Here we are at a computer science conference. You've probably been to quite a few. This is arguably the first, perhaps not a conference, more of a summer school, a 6-week summer school in computer architecture from 1946. The reason I'm showing it to you is because of this guy here, Professor Eckert, and this machine to some extent, the ENIAC. ENIAC was a reconfigurable parallel computing machine. Amongst the people associated with it was John von Neumann, who's often credited with inventing the stored program concept. He invented it, there's documentation to show that he could figure out how to make this a fetch-execute machine. They never did. They never did because it was in production, and it would have computed less quickly as a fetch-execute machine as it did as a custom configurable machine. If you look around that room, who knows what it is? Here's a map, or a computer architecture diagram, depending upon the way you choose to read it. And what you see is that there are lots of copies of things like multiplier 1, multiplier 2, multiplier 3. It really is a parallel machine. Here are people programming it. I don't know for sure, but I think what she's holding is something like this blueprint here, this wiring diagram. This is how you program such a machine. The reason I'm showing you this is because of this quote from the proceedings from that conference in 1946. And so it says, again I wish to reiterate the point that all the arguments for parallel operation are only valid provided one applies them to the steps which the built-in or wired-in programming of the machine operates. Any steps that are programmed by the operator who sets up the machine should be set up only in serial fashion. And this is my favourite part. It's been shown over and over again that any departure from this procedure leads to a system too complicated to use, over and over again in August 1946. So what do we know that makes us think that we can do better? What have we learned since August 1946 that tells us that we can somehow tackle this problem? Actually, there are lots of interesting answers to that question. For example, at that time, nobody had ever written a program that produced a program as its output. Nobody had written a program generator, nobody had written a compiler. So there is hope. So, this talk is mostly introduction, different ways of coming at it. What I want to talk about is that compiling idea. I want to talk about this. It's an English cliche or proverb. Can you have your cake and eat it? Can you have your cake and keep the cake and enjoy it tomorrow? Can you have two inconsistent things at the same time? It's a recipe for practically every grant proposal you'll ever write, probably. So there's the cake. This talks about the idea that we might simultaneously raise the level at which programmers reason about their code, write their code, think about the reuse of concepts and the abstraction, and simultaneously provide the compiler with a model of the computation that enables it to generate faster code that you can reasonably write by hand. Now this is a bizarrely double-edged thing, actually. One perspective is, this is actually what every compiler does. This is what compilers do. The other perspective is to say that you have become used to abstraction that raises the level at which you think being a barrier to performance. And that's the bit I'm interested in, actually, is how can we actually turn that abstraction to performance advantage? And that's, to some extent, the whole domain-specific language story. So can we get higher performance than you can reasonably expect by hand by what? By delivering reuse of expert techniques. So we may know cunning ways to implement particular classes of problem. Let's package them up in a program generator and drive it from an abstract model of the computation. I'll show you some examples of that. Can you implement aggressive or disruptive optimizations? So optimizations where you know that really going for it with heavy-duty, large-scale analysis of the computational graph can yield a payoff that no normal compiler would invest in. You might know this because of properties of the application. I'll show you an example of that. Another one that I quite like is disruptive optimizations. And this is particularly, I think, applicable in parallel programming, where parallelism issues tend to be cross-cutting in some sense. So if you think about the distribution of data, if you're computing on distributed data, then that management of the distribution of the data is going to cut across all the code that operates on it. And so you see that very commonly what you need is for your optimizations or your compiler system to somehow generate a piece of code that is woven with those concerns from code which is somehow simpler and separated. Obviously, we also look for this, performance portability, a big buzzword, the idea that not only can we get performance, but we can get isolation of the long-term values embodied in the higher levels of the software from the optimizations needed for each individual platform. And the contrary is that you hack your code for today's platform, and in some sense you destroy its value carrying forward, moving forward. Another one that I like, and I think is worth looking for, is raising the level of abstraction. Abstraction is So I once came across a detective story with the quote, "Someone has abstracted my wallet." Abstraction, not everybody's a fan. Sometimes it's just the right abstraction that is important, and having some level of good taste and good engineering in choosing them is perhaps the real art behind all this. Another one that I think is nice and comes from that is domain level correctness. The idea that you might catch bugs because of your abstraction. And a classic example of that would be to think about a type system that distinguishes mathematical objects in a way that their representation does not. So, right. So that was some of my introduction. The other thing I should do is say a bit about what we're doing in my research lab. And we're trying to do, this is a map of things that I imagine we might do, not so much necessarily things we're doing all of. So at the top we have some very high level or fairly high level domain specific language projects. And at the bottom we have some diverse hardware that we're interested in. So obviously, like everybody else, we're interested in graphics processors and multi-core and large clusters with MPI. I'm very interested in vectors and vector processing. Partnering with this is sort of the same issue. We also have a relationship with a local company, Maxella, who do streaming data flow machines implemented in FPGAs, which I think is a really interesting way to rethink what it means to be a general purpose computer. The point, of course, is the performance portability story. We want to give you some kind of isolation between what you do up here and what happens down here. And so in between, we have some layered domain-specific language tools. And quite how domain-specific and what that really means depends upon the layer. So a key layer here is, for the sake of argument, it's been called OP2, which is really the name for this narrow, specific thing. And that, in turn, is the name for a project in collaboration with Mike Giles. Are you here, Mike? Yes, there you are. So you will probably resist any of the ambitious extensions that I'm listing here. Or perhaps insist that they be given some separate name, lest they fail horribly. I'll show you what so actually, this layer here is, I've called it OP2 on this slide. I'm going to talk about, this is where the access executed descriptors from the title come in, and I'll show you that in a little while as well. So above this, so you might program directly in this layer, and some people do, some people will. We have applications then that you might program directly on this layer, and then we have domain-specific tools, so applications like this one, for example, programs directly to OP2. But then we have tools like this one, where there's another compiler that takes this unified form language that I'll show you in a little while, and maps that down onto OP2. So we have a layered structure of domain-specific languages. And I don't know whether, if you do DSL stuff, you're going to do the same thing with that layering. The thing to think about is that the DSLs in question are very different. Essentially, OP2 is, in some sense, it's a do-what-I-say tool. And UFL is much more declarative. Well, let's move forward and I'll show you what I mean. So, this is, it's early in the morning. You could just stop here and take away what I think is the message from my talk. Let me try and show you what I hope you can look out for when we dive a bit more deeply into the specifics. So, slogans like generative instead of transformative optimization. The classic idea with an optimizing compiler is that you take code the programmer wrote and you transform it. If you think about a kind of DSL perspective, you hope that you have a higher level representation from which to start. And so really what you want is to generate the right code in the first place. That's what I mean by generative. And if you can do that, then you can save yourself the trouble of working in a transformative way. Which doesn't sound like a big deal. It's truly vital when you think about the composition of optimization ideas. So if you optimize a loop nest by transforming the abstract syntax tree for the loop nest, the next optimization has to deal with what this one did. And if you can figure out how to generate the right code in the first place, I think you have a much better handle on how to control the complexity of what happens when you have lots of optimizations operating together. Get the abstraction right. This is a more subtle understanding of that, because the reality of this one is that it's not truly about always generating the code. It's about thinking about alternative code synthesis possibilities at the right abstraction level. Yeah? So a nice example of that, we did a project on loop fusion in linear algebra. And the first version of this code was for dense linear algebra. We generated the abstract syntax tree for adjacent loops, and then we had a pass that operates at that level and does loop fusion, and it worked. Then we modified the DSL to work on sparse linear algebra. And conceptually, nothing has changed. The loop fusions should be just as valid as they were before, except that this abstract syntax is a complete mess. And our loop fusion pass won't work anymore. What do? Well, you realize that you started from a graph that talked about matrix vector multiply instead of loops. And if you do the fusion at that level, everything's fine. Build vertically, learn horizontally is to do with the idea that we're trying to do compiler research. We're doing narrow domain-specific stuff, so the compiler people kind of don't want to talk to us. The reason we're doing it is in order to break the barriers of what's possible in conventional compiler technology, and having done so, generalize. So, I hope along the way you'll see some of the answers to these things. This is just, those compiler people. There's a long history, mostly from the last century, of climbing the analysis hill and then generating code. And a huge amount of the textbook is devoted to this half of the picture. The reason I'm showing you this is because actually I think one of the big discoveries of the last 10 or 20 years in compilers is that all the fun is on the downhill side. And let's see if we can actually do this downhill. Let's get a helicopter right to the top and ski down. Here's a ski map showing all the different code synthesis alternatives, routes down the mountain. And the point is, don't get distracted by this stuff, start at the top. And if you do that, the higher you start, the more you can reach. The bigger the space of code synthesis possibilities. And again, when you think about going higher and higher, you realize that things tend to change in their nature as well. So there's a rich world of domain-specific tools for talking about particular classes of rich data structures. And commonly, you have, for example, parallel computations on unstructured meshes, which we'll show you, or graphs, or some such thing. And that's one family of such tools. And in some sense, they do what I say tools again. You're telling the computation how to compute on your data through some abstract data type. And then there are a lot higher level things, somehow specifying application requirements and leaving the implementation to select potentially very radical things. Often these are kind of procedural, and these are more declarative. And I mean that beyond functional programming. Right. So what should we hope to see in the DSL? We expect to see some raised abstraction. We expect to see that you capture a domain of variability. So this is a funny diagram, and I wish I knew how to draw it better. Now here's your DSL, some unifying representation for a class of application problems. And there's a knob here that lets you adjust the input to span some range, some domain. And of course, down the bottom, there's an ability to span some code synthesis space. The whole point of domain-specific is that these are not completely general, and there's value from being focused. The question, of course, in embarking on a DSL project is to ask yourself, what is the domain? Does the customer care about the variability that I'm introducing? Am I actually getting some payoff from narrowing that scope? So we're trying to capture that design space, and we're trying to match implementation choice to application context. So actually that's what optimizers do with compilers. Non-optimizing compilers are easy to test because they generate code in isolation that doesn't depend upon the context. Once you start doing complicated things, you start weaving the context into what code corresponds to each feature in the source code. So, that is 25 minutes into my talk, and mostly the introduction is done. What I want to do now is show you 2 or 3 different DSL projects that we've been doing. And we don't really have time to get to the bottom of the science or the detail of the results. The reason I'm doing it is to try and illustrate some of the things that I've just been saying. Incidentally, there are many empty seats, and there's a queue of people without them over there. I hope you can just come in and sit down. So let me begin by showing you a project that we finished a few years ago. And it's a project with a company called The Foundry, who are based in London, in Soho, in central London, where there's a whole network of companies servicing the film industry, the film and TV and advertising industries. And The Foundry do plugins for compositing tools for video post-production. This is post-processing of photographic images. They have a team of experts building complicated C++ implementations of research papers in image processing of various kinds and delivering them as products. They came to us to figure out how they should tackle the exotic architectures problem of SSE and AVX and GPUs and whatever comes next. And what they wanted to do was to redesign the, in some sense, image processing primitives on which their code was built. And one of my PhD students, Jay Cornwall, came up with this, which they are in the process of, well, they might commercialize it. They said they would. I think they're busy using it to build products, actually, at the moment. So here we have, so there are 2 slides here. This one is about kernels, and the next slide is about how the kernels are composed together. So here's a kernel. It's a little bit like a functor in C++, actually. Here's the code for the kernel that actually computes something on a pixel. And what you see from this picture over here is that what it computes is 2 outputs, here they are, and it computes it from an input which is a stencil in the vertical axis, a stencil of some radius. So it computes, using that stencil, produces values for 2 points in 2 different output images. The reason I'm showing you this is that this construction here, this indexer thing, captures this picture. What I mean by that, without going into all of the detail, is that it precisely characterizes the dependent structure of the kernel. So the implementation will launch this kernel on an image, but it knows exactly what the pixel by pixel dependent structure is. Now, here is a piece of code that uses the function that I just showed you in the context of a bunch of other similar things. In fact, this particular function, degrain recurse, it's an image degrain filter. It's for removing photographic grain. It's actually recursive. It consists of a whole bunch of image-by-image operations. What we did was it's one of my favorite tricks. It's a functional programmer's trick. It's a lazy evaluation trick. So you know this story, right? We delay execution of all of the stuff in there so that by the time you've finished executing degrain recurse, you don't have an image, you have a graph. You have this graph. Yep, it's a graph of whole image operations. But every time you called one of these, it gave you, in your graph, pixel by pixel dependence information. That means that this graph tells you how every single pixel in every single one of those intermediate images depends upon all the others, precisely. With no analysis. You probably could have done this sort of thing by analysis. This is downhill, right? The programmer gave us it. The programmer knows we have it. It's robust. You don't trust that the compiler can figure it out. So what do we do with that? Well, actually a simple win turned out to be really nice. is you just walk this DAG and find the minimum space execution sequence for it. Which, if you think about it from this point of view, it's quite just, if you try and optimize for space in this code, it's quite messy. It turns out to be really simple just to walk this and choose the sequence that minimizes space. Also, it turns out the graph's quite small, you can do it exhaustively. Then what we did, of course, was build various parallel implementations. The main thing we focused on was SSE and multi-core and CUDA GPUs. So here, taken from some papers, are some performance results. Two different applications. On the left is the degrain filter that I mentioned, and on the right is is another application that's well, the good thing about the degrain filter is that you can do loop fusion on each of those operations in that graph. So you can obviously generate SSE code because it's image processing. If you just generate SSE code, you don't do loop fusion, you don't get any performance advantage at all because it's completely memory dominated. In this case, we were able to do massive loop fusion in this example. And actually what you see from the results, I think the most interesting graph is that one. So these are slightly old processors. But that line there, there's two of them together. One of them is an 8-core Core 2 machine, and the other is an NVIDIA GPU. And they have matching performance. Because actually when you work out how many flops the two machines can do, they're flop limited and they have the same flop limit. And the loop fusion has meant that it's the flop limit that counts. If you go over here, where we were unable to do loop fusion, the GPUs are up here, and the CPUs are down here, because this is completely memory bandwidth limited, and you can pretty much predict that outcome from just looking at the memory bandwidth of the two machines. There's a breakdown of the different optimizations here. So this is, as I said, being commercialized. Is it a DSL? It's a library. It's a bit of both, right? It doesn't matter. Whether it's a library, an active library, a domain-specific language, an embedded domain-specific language, these are all ad hoc deployment questions. The point is to get the advantage that I talked about by fair means or foul. Right. So, when I talked about the big picture of what we do, I showed you a picture a bit like this one, and in the middle was this OP2 layer, and I said this is the access execute layer. So the question in my mind really is, what do we have to do here to make this a common representation that will handle a very wide variety of different projects? Now, I should be careful because this is classic computer science, right? You have a way of building a high-performance implementation like the one I just showed you, and then you say, aha, that's no good. What you want to do is generalize it. You want a general framework for building domain-specific tools. Maybe you should have been happier just building good things. But I think, with respect to that ambition to do something which is actually relevant to the larger compiler's picture, we should ask that question. What should it look like? What should that layer look like? What do we have to do in here to make all this other stuff work? And my answer, and what do we have to do in order to refine that question, what I want to be able to do is this. I want to be able to automate the synthesis of all the data movement code. Right? So I want to say, I'm going to execute this iteration, this loop, on this processing resource, and in order to make it happen, I'm going to have to move the data that it needs to there. Possibly through an MPI message, possibly through some kind of tiling or staging into scratchpad or shared memory or something. I want the compiler to take all that away and figure out from the iteration space and the access properties of the individual iterations what the data movement should be. And partition and parallelize and schedule the execution of the loops, possibly select storage layouts, perhaps use that dependence information to do loop fusion. If you're going to do loop fusion, you'd like to contract intermediate array data structures as well. They're arrays, whatever they are. What do we have to do? We have to explicitly characterize which data will be accessed at each point as a function of its position. And that's what we did in the image processing example. And this is what I mean by this access execute descriptor idea. Now, I claim that's a functional programmer's idea. The funny thing is that when I talk about, so what we're doing is we're precisely characterizing dependence. We're precisely characterizing which locations will be read and which will be written, which means we need to talk about overwriting things as well. So here's a sort of religious thing to say. You know, functional programmers shouldn't be scared of overwriting. The important thing is to have precise knowledge of what that dependence structure is and not have to hunt and analyze to recover it. Sometimes, for example, if you're computing on a multi-gigabyte mesh, it's important to know that you only need one copy of it because you're going to update it. So what does this mean? It means we need to separate the execute part from the access and write back. In fact, this is what streaming is. Often people think of streaming as being, well, it's a vector operation. You have stride one stepping through your data. Actually, in general, the only thing that really matters is that you can separate the access, the address generation, from the compute. If you can do that, it doesn't matter whether those addresses are in some nice sequence or what. The important thing is that you can hide that latency, you can move that out, and you can let the compiler synthesize whatever code is necessary to do that. So what we're talking about is characterizing the iteration space, and characterizing a read footprint and a write footprint per iteration, and generating the code from that. The trick then is to apply that idea in different contexts. I believe that you might have seen that that's what we were doing for the image processing example. Let me show you another one. And this is the OP2 project that I mentioned to you. So just for motivation and pretty pictures, here's an image taken from a colleague of mine, or rather the Applied Modeling Computing group at Imperial College, in particular Gerald Gorman, I think. I'm using this to motivate the idea of an unstructured mesh for doing fluid dynamics. Let me just stop this for a moment. Damn, it's worked before. It won't stop. How do I stop it? That was a mistake, wasn't it? That really was a mistake. The reason I'm stopping it is just to look at that mesh for a moment. It's discretized, continuous fluid. And so what's happening is there's a fluid coming in from the left, past a heated cylinder, and what we're getting is complex eddies in the wake. This mesh here is being adapted. In this case, it's being adapted continuously at runtime. In many interesting applications, it's adapted. It's carefully constructed at the beginning and not changed afterwards. But what's important is that because we're doing this with triangles, the adjacency relationship doesn't have to be uniform. In a regular mesh, a mesh of squares or cubes, the adjacency relationship has to be completely uniform everywhere. The freedom that this mesh gives you is to be able to adjust the density of the mesh smoothly. The price to pay is you have to follow pointers in order to figure out what's next to what, and therefore what data, and therefore to access the data that the computation needs. It's coming, right? Yes. So, what we've done, what Mike did, and we've been following up in some sense, is designed this OP2 representation with interfaces from Python, C++, and Fortran for a simple thing. It's a parallel loop over a mesh like that one. Actually, a mesh without the dynamic adaptation. We'll do that another day. Okay? We're working on it, but currently OP2 assumes the mesh is not changing. The reference implementation is code that you can just compile and run. It's a library, it doesn't go very fast. But then we have various faster implementations that can generate CUDA, OpenMP, MPI, we're working on AVX, and we're playing with FPGAs. And it's an instance of the access execute idea. So the parallel loop has access executors. Let me show you. Here is code. I hope you don't mind. This is C++ code. It really works. On the left is the setup for the mesh, and on the right is a piece of code with two parallel loops in it. On the left, we set up, so the OP2 model for a mesh is actually a really simple thing. It's a really flat thing. It's an iteration space, a set of nodes or edges, which actually has no data in it. It's just an iteration space. And then we associate with these iteration spaces, these sets, maps. For example, a map from edges to nodes. This is the map from the left edge to a node. So if you think about an edge in the graph, it has vertices at the two ends. It has nodes at the two ends. And you have a map that takes you to the left one, and a map that takes you to the right one. Then you also have data. You have data associated with the edges, and data associated with the nodes. So when you write a parallel loop, you can either visit the nodes, or you can visit the edges. If you visit the nodes, then obviously you have direct access to the node data. If you visit the edges, you have direct access to the edge data, but you might want the data from the nodes that this edge connects. So over here we have two parallel loops. This one iterates over edges, and this one iterates over nodes. And this one's the interesting one, I think, because this is the one that follows a pointer. And it follows a pointer through, so the function that's being called is res. Let me just show you that code. Where's it gone? Here. So res is just a little piece of C, and this little piece of C has 4 more parameters, and it computes on them and produces a result. These are the access descriptors. And the access descriptors declaratively specify the way data is to be collected from the abstract mesh and passed into the code. Right? So notice that this is not a description of what that code does. This code doesn't access memory. This is a declarative specification of what data has to be fed in order to execute that. Right? And again, what we're trying to do is to spoon feed your tools with stuff it should know. Stuff your tool should know, so that you can have confidence that it will robustly be able to do good things with your code. So this access descriptor says that it accesses the data associated with the PA, which is edge data, and accesses data PU associated with the vertex reached through one edge and P du through the other edge. And the access mode here says that it reads and reads and it increments. As you can see in the code, du is incremented. Right? So if we want to do all the iterations of that loop in parallel, we have to think about the critical section due to that increment. Let's have a look at how you implement OP2 on, for example, the graphics processor. You need to take your mesh. I've made it a bit regular here just because it was easier to draw. Partition it somehow, as I've shown. And so then the partitioned representation of this is going to be partitioning of the edge sequence, of the sequence in which the edges are stored in memory. So this partition here is a contiguous block. If we want to execute that edge loop on that block, then we fetch the edges, because we need the edge, or rather we fetch the data associated with that region of the edge set. We also need the data associated with that region of the vertex set. That's easy for the inside bits. So each of these edges has a map to the two vertices in question. Some of the edges map to vertices that are inside this partition, so here they are, and some of them map to stuff that's on the boundary, and here they are. So the implementation here is going to load the edge partition into the graphics processor's scratchpad memory in a nice contiguous vector block. It's going to do the same thing for the inner region of the vertex block, and it's going to have to do something different at these cross-partition edges to mop them up, but hopefully that's a smaller part of the problem. Once you've got that data in shared memory, then you can compute in a nice data parallel way, following the edge pointers to their shared memory copies. Of course, because of that increment operation, you have to think about the concurrency control. And so the implementation not only does partitioning, but also coloring. It separates the set of edges so that no two blue edges share the same vertex. That means you can do all the blue ones in parallel, and then you can sum those results into their corresponding vertices, and then you can do the green ones. Now, what I'm telling you about are code synthesis choices that we made for the graphics processor. I think they work pretty well for OpenMP as well, but we're thinking about that, and the point is that different targets will have different code synthesis alternatives, different optimizations. There's much more you could do. If you think about a sequence of loops, you might hope that when you've loaded a partition into the shared memory, you should be able to do more than one loop body on it before you move on to the next partition. And that precise dependence information should tell you how to do that. So this is what I meant by the access execute model. We saw it in the image processing case where the access descriptors were actually rather simple. They're essentially affine expressions. Here, the access descriptors are with reference to the maps, to the pointers in your mesh representation. So this is an example of a DSL that computes on an abstract data type and exploits properties of the abstract data type in order to generate good code. And to do things, so classically compilers will give up when they see the indirections associated with this. But we know what's going on, and so we should be able to do better. So I'm going to run out of time if I take you through the performance numbers for this, and I kind of wanted to show you something else. So I think what I'd like to do is to skip to the third and final domain-specific language project. And this slide is a bit too complicated, but let me just try and use it as a map of what we're doing. So I mentioned that we have a two-layer story for a class of partial differential equation solvers for finite element techniques. OP2 is in the middle, but at the top is a thing called the Unified Form Language. It's a DSL. It's a DSL that we didn't invent, which is a good thing. If you're going to invent a DSL, you should definitely ask yourself whether there's somebody who's got one they're already subscribed to. And so there's a whole world of people, actually, from the Phoenix project, based at the Similar Lab and elsewhere, who've already signed up to UFL as a way of automatically generating code to solve partial differential equations. And really what we're doing is building a new compiler that starts from the same representation, but goes via OP2. So we didn't invent it. We've done things that plug in at various steps. Now, what does UFL do? This is too small to read, so I've expanded it here. Look at the shallow water equations, partial differential equations for modeling, for example, tsunamis. UFL is kind of a Python transcription of that representation. So if you look, you can see the vector calculus differential equations in here. What this is doing is pretty much a transcription of the algebra. It's characterizing exactly how the PDE, or what the PDE is, and how it's to be discretized, the solution. So curiously, what UFL really does is this is only half of the DSL in a sense. This is the half that tells what PDE to solve. The other half is what element to use in solving it. And the code synthesis uses the element to compute how the flow state is approximated on each of those triangles, for example, in order to set up the system of simultaneous equations that needs to be solved to represent the conservation laws, essentially, of the PDE. So what we do is, from here, we generate assembly code that assembles the global system matrix. We apply this at every element, every triangle, every edge, depending on exactly what your discretization is of your mesh. And the result is a matrix. So here's your mesh, you visit a triangle in it, you run that assembly code, you get a local assembly matrix, and then you disperse that, you distribute that into the global stiffness matrix. That's the classic finite element story. The reason I'm showing you this is because actually hiding in here are some quite interesting implementation alternatives. And one of them is whether even to represent that matrix at all, or rather whether to construct it. Because what you could do is run that assembly code, get each of those little dense local submatrices, and essentially keep an array of them, and use that as your representation of the global system instead of actually constructing a big sparse matrix. The good news is, this thing is a highly structured data structure, whereas the sparse matrix has a non-zero structure that depends on the mesh. And the mesh we chose an unstructured mesh in order to have a non-uniform adjacency relationship. That means that the matrix is going to be unstructured and messy, and going to be difficult for high-performance implementation. So the algebra here basically says that when you run your iterative linear system solver, instead of doing a matrix vector multiply using a compressed sparse row representation of the matrix, let's do a matrix vector multiply using that representation of the matrix. Sounds great, except that this is bigger, and there's some work that has to be redone every time you do it to resum the values that are actually mapped to the same entries, the values that couple the triangles in the mesh. So the question you might ask is, why would this be a good idea? It does more work. In fact, it moves more data. But it moves data in a nice, organized way. There's a nice storage layout, which should have very high efficiency usage of the bandwidth of the system's memory. And the amount of redundant computation depends upon the amount of coupling between terms in the problem. And that is something you can control if you think about a higher level representation of the problem. So I said that UFL is a combination of the PDE and the discretization. The discretization is about how the fluid state is approximated across a triangle. And that's a polynomial approximation. The order of that polynomial, P, could be low or it could be high. If you make it high, then you have lots of essentially sample points across your triangle, few of which are coupled with the neighboring triangles. And so by changing P, you can change the size of those blocks and the amount of coupling that takes place in the matrix, and therefore the amount of inefficiency introduced by this trick. That means that as you change P, and here's an example from some work we did with Spencer Showings and Chris Cantwell at Imperial, comparing the local assembly scheme, green one, with the global assembly scheme. The global assembly scheme is where you build the compressed sparse row matrix. And the green one is where you can build that block-wise matrix, and then you recompute the vectors for every matrix vector product. What you see here is as you increase the polynomial order for the finite elements, so it's all normalized with respect to the local scheme. The local scheme looks really bad when P is low because of those redundant additions that you keep redoing. But as P gets larger, the memory performance advantage gets bigger and bigger. This is on an Intel Core 2 processor. Our experiments on GPUs show that actually this flip here, from where green is better, from where blue is better to where green is better, we think that that is shifted to the left, so that for almost all P's, you should go for local matrix, local element if you can. Okay? So I'm showing you this to try and to try and expose the idea that, well, that helicopter ride, as it takes you higher and higher, opens up more of your code synthesis space. So this really isn't something I think you can reasonably expect your Fortran compiler to do for you. It is a safe thing to do. It's numerically producing precisely the same result. Changing P doesn't, but switching from local to global produces exactly the same result. It just actually recomputes things. So it's kind of within the domain of what compilers should be allowed to do. The trick is to get them to do it. And that means we have to start at that higher level representation. And things like this are the payoff from doing that. Where that trade-off lives depends upon your application context. The red ones, incidentally, some factorization are a third alternative, and you need to read the paper to see how that works. It exploits an orthogonality property in the local matrices. This is the last technical slide, and we should get to questions in a moment. Because the key to all this, in my view, is, well, what we want to do, of course, is to get the compiler to automate what the compiler has the right to automate. Stuff that doesn't change the answer. Of course, changing P does change the answer. It shifts the applicability of your solver depending upon things like properties of the smoothness of the solution. What this graph shows is quite a tricky thing. It shows, here's increasing P, and here we are increasing the mesh density. Okay, increasing H. So often you read about HP adaptation in PDE solvers. So you can achieve a given level of accuracy. And here are the accuracy levels. And you can do that either with low P at high mesh density, or you can have a low mesh density but use a high order polynomial. Right? Of course, which of those is better? Which of those is faster? Well, that's what the blue curves are showing, is the execution time of those solutions. And actually, what you should do depends upon what accuracy you're aiming for. How you should implement it depends upon whether you're on the left or the right-hand side of that blue-green divide. And what you want is for your implementation, for your tools, to allow you to navigate that solution space, pick the H and the P combinations that you want, and generate the right code to optimally exploit your hardware for your particular problem. It's not just about automation, it's about putting the tools into the hands of the users to give them the means to navigate that solution space. Okay. And that brings me to the end by just concluding with things I've probably told you many times already now. Algorithmic choice makes a huge difference, and the best choice depends upon the target hardware and the application context. We want to automate code generation so we can freely navigate the solution space and put those tools into users' hands. Thank you very much indeed.
Many thanks to Paul for this very entertaining talk. I'm sure there are quite some questions in the audience.
Thank you. If we have a program representation that gives us a very detailed, very precise graph of dependencies that have a very high, a very fine granularity, we come into the following problem. If we're trying to map that onto hardware, then we need to pick the size of a unit of the program to be scheduled, because if the granularity is too fine, the scheduler will have a very large search space. So how do we pick this unit of scheduling properly?
So I argue that you should have access to an element by element, iteration by iteration dependence representation. The question is how you use it. And so, for example, in the GPU implementation for OP2, the access descriptors give us that information. They don't give us to it at compile time. They give us it, they tell you how to calculate which data each iteration will depend on, given the mesh, and you don't know the mesh till runtime. So what the compiler has to do is generate code that partitions the mesh and figures out what the halo will be. And the halo tells you the partition-to-partition dependence. Right? So at runtime, we compute on the mesh in order to determine the dependence. At compile time, we generate code to do that, and then we generate code that assumes we've done it. You see what I mean? So in the end, yes, we do, at runtime, manipulate iteration by iteration dependence, but we don't do it at compile time. We don't even know it at compile time. But you can choose that partition size depending on your machine.
So I've got a social process question that I'd like your opinion on. So I drink all this Kool-Aid, and I particularly love what you said about the fact that you reused an existing DSL, and that we should all do the same thing. So what I'm worried about is that the scientific process works well when there's an opportunity for incrementalism. So I think we need to find a way to get past individual PhD students deciding they're going to do a GPU language as their project and kind of making it up all as they go along. Because when you get a whole pile of people together who all work on a JVM implementation or vectorizing C code, they can talk to each other and build incrementally. Whereas if you take slides, I believe like your slide with all the boxes and with MPI and CUDA at the bottom, and you intersect that with, say, Kunle's slide that has almost the same layout, I think the only intersection is MPI, CUDA, and OpenMP. So how do we get something in the middle that we can share?
Yeah, you're right. So I kind of facetiously said that it's a computer scientist's neurosis to look for that generalization. Of course, it's an elementary software engineering strategy to try and build some kind of common core simply to support interoperability between different domain-specific tools, for example. Is that what you mean?
Oh, sure, and then give the name and document it and let's share it.
Yeah, I mean, I might have waxed lyrical today, but I can get a lot more lyrical than this. My ambition is that we start building domain-specific languages that are not just software tools, they're tools for communication and interoperation, or in some sense, conceptual sharing between people at the top of that hierarchy. Yeah, so that they can realize that their numerical methods have things in common, and common concepts and common capabilities and opportunities to interoperate. And that means, of course, that the infrastructure has to support those connections.
We have time for one more quick question. Okay.
Fritz.
Technical question, actually, or general question too, we'll take that offline, but on the grid, the unstructured grid approach, you had chosen the coloring, edge coloring, so I would imagine with grids that have few nodes with enormous amounts of in-degree or out-degree, this will not be the optimal algorithmic strategy. Yep. So have you experienced that, and would you then, node replication and various strategies that have you seen feedback coming back, in the sense of the implementation strategy is fine for the instances we're seeing, but it's not good enough because some new instances coming in. I don't know.
So your question is, I'd slightly assumed that the mesh we're computing on is, in some sense, if not actually uniform, it's mostly uniform, in that the in-degree is not wildly varying. And if it is, then you could imagine that this coloring scheme would involve a large number of colors. Of course, in fluid dynamics applications, the mesh is adapting smoothly, and so your use of that variability of the edge mapping is relatively under control. There are applications where that property isn't so clearly held. A nice one might be if you think about the neighbor relationship in a system of particles, where some of the particles are very big. So we have people modeling things like sand, where you have big lumps of sand, big grains, with many, many, many neighbors. And there, I think you're right with this strategy. might be problematic. An alternative strategy might be to use, say, the GPU's atomic instructions. My guess is that you simply get contention there as well. So yeah, I'm not quite sure what the best solution is. There are, for particle problems, there are ways to handle this simply by changing the way you do the addition phase of the algorithm.
A quick follow-up. I mean, clearly, actually, this seems like the right separation of concerns because it's not in this modeling of sand or of fluid dynamics that actually the edge coloring pops up. But is it your experience that that application scientists are happy about this division of labor, or wouldn't they rather sometimes hack the Fortran code themselves to make sure that they get the right kind of edge coloring, or at least paired up with edge coloring?
That's a really nice question. So let me think. I've given you all sorts of reasons why DSLs are a great thing. You've probably yourself made the decision not to use exotic tools, and there are good reasons not to adopt things like program generation tools. The classic one is it's a walled garden. If what you want to do is inside, you're fine. If you want to do something that takes you outside, you've broken the abstraction layer. It's a mess. So you have to build tools which are somehow hackable. I think you can't escape from that. The box has to be open, the APIs have to be present, and it has to not completely destroy the structure of what you're doing. If people want to program in UFL, but occasionally mess with the mesh directly, for example. Right, that's fine. There was another thing to say. Yes. One of the things that we learned from the engagement with the movie post-production people was that the relationship was not you guys operate on one side of the library and we build in the library and supply it. The relationship instead was we design the software technology to give you the separation, and you have a team up here and a team down here. And the consequence of our engagement with the Foundry was that they had an HPC team that they didn't have before because it could focus on what happened inside. And so you have domain experts, but you have them in some sense separated. So you need to give them that control.
Okay. Then let's thank Paul again for his nice talk.